Okay, let's take a quick look at square roots. What are they and how do you use them? Now before we look at square roots, we kind of need to know indices first. Now indices, it sounds like a tough word, right? It's really simple. It's just a number to the power of something. 2 squared is an indice. What does 2 squared mean? It means 2 times 2, so it'd be 4. 2 to the power of 5 is an indice. What is it? 2 times 2 times 2 times 2 times 2. 2, 4, 8, 16, 32. What's 3 cubed? 3 times 3 times 3. That's an indice. That's 27. So these are indices. Now, you know how there's plus and minus? You can reverse adding a number by minusing it. You can reverse multiplication by dividing it, right? We can reverse indices, squaring a number or cubing a number, etc. You can reverse a number to the power of something by reversing it. You can reverse it using roots, square roots. Now, what exactly are square roots then? Square roots, if you want to write them more like a proper definition or more detailed, you could write square roots like these, like this. What does this 2 mean? We usually remove the 2 because 2 is the square roots, basically means what 2 numbers can multiply to make the number below the square root sign. The square root sign is basically just a tick with a long line coming at the end of it. So 5 times 5 makes up 25, right? 5 squared. That's where the square comes from. The square root of 25 is 5 squared, which is 5. We also have cube roots. So for example, we could have the cube root of 27. This means what 3 numbers multiply together to make 27, the number below the square root sign. Well, 3 times 3 times 3 makes up 27, right? And this is also 3 cubed. So that's why it's cubed, cube root. 3 numbers that make up 27. So the cube root of 27 would be 3. So this is basically what square roots are. It's 2 numbers. For square roots, it's 2 numbers that you can multiply together to make up the number below it. We usually simplify the square root sign, 2 sign here, because 2 is the most common one. So this is basically the default. We also have cube roots. For cube roots, anything higher than square roots, you have to write it because you need to be able to differentiate the different ones, right? Cube roots, 3 numbers. You could have the 4th root of something, 4 numbers that make up the number below it. The 5th root, so on and so forth. You could have 5 numbers that make up the number below it. That's basically what these are. Okay, let's take a look at an example of a bit of a tougher question. We could have 5 cubed, all raised to the power of 5. How would we do this? This isn't really square roots. This is more similar to indices. So what's 5 cubed? 5 cubed is 5 times 5 times 5, right? This is all being raised to the 5th power. That means we have 5 of these, the set of 5s. So 5 times 5 times 5. We're not just going to add these powers to make 5 to the power of 8. This is not correct. You have to multiply them to get 5 to the power of 15. Why is that? We have 3 5s here, right? Imagine we have another 3, another 3, another 3. We have 5 sets of these. So 1, 2, 3, 4, 5. These are all 5s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We would have 15, 5 to the power of 15. So imagine these are all multiplied together and these are all filled with 5s. This is how you answer a question like this. You don't add these powers. Same with just normal multiplication of powers. 5 to the power of 3 multiplied by 5 to the power of 5. You would just add these powers. 5 to the power of 8. Why? Because this is 5 times 5 times 5. And this is 5 times 5 times 5 times 5 times 5. So how many times are we multiplying 5? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 lots of these. We're just multiplying 5 to the power of 3 by 5 to the power of 5. This is different to this because we're multiplying the set of 5 to the power of 3. That's why we're multiplying this to get 15. We don't add it. Because of the brackets, we're multiplying this set of 5 cubed. This time we're just multiplying these individual ones, so we just add the powers together. For division, division is pretty similar too. If we have, imagine q. Q could be any number, right? Q to the power of 8 divided by q to the power of 3. What do you think we do? For multiplication, if we had q to the power of 8 multiplied by q to the power of 3, we would add the powers, right? So we'd have q to the power of 11. Same way here for division, what do you think would happen? Division is the opposite of multiplication, right? So we would do q to the power of 8 minus 3, making us q to the power of 4. Sorry, q to the power of 5. Okay? You just minus the powers for division. Another example. Q to the power of 8 divided by q to the power of 3, right? How can we visualize this? Well, we have 8 on top, so you can make a division sign, right? So we have q times q times q. This is going to take a while, q. But it helps to visualize this, to help you understand. 1, 2, 3, 4, 5, 6, 7, 8. In essence, this is what this is representing. 1, 2, 3, 4, 5, 6, 7, 8. Q to the power of 8. 8 q's multiplied together, divided by 3 q's below. What would happen? Well, for any fraction, you would cancel out and simplify, right? So this cancels out with this cancels out with this, and this cancels out with this. That leaves us 1, 2, 3, 4, 5. Q to the power of 5 over 1, which is basically q to the power of 5. The same way we could have just done q to the power of 8 minus 3, giving us 5. But it sometimes helps to visualize this so that you can actually understand the concept. Anyways, that was an intro to indices and square roots. And next video, we'll look at negative indices and fractional indices. Thanks for watching this video.